Welcome to Science Sunday. It's helpful in any mental endeavor to state one's premises up front. Scott and I have talked about this a number of times. We believe there's no such thing as a bad question. We draw a distinction between the premise and the fact that the number of bad answers are uncountable. We also recognize that science in all its forms, biological, astronomical, geological, psychological, economic, and social, is really the only viable means of separating good, accurate, and truthful answers from fantastical, mythological, or just uninformed ones. Science Sunday started in 2012 here at the DuPage UU Church. We continue to be grateful to the church for providing us a place to meet on the first and third Sundays of the regular church season. And thank you for coming. We invite you to explore science here and share any knowledge you may have about nature and the cosmos. We also invite you to explore this community of science lovers, many of whom are members of the church. We hope you will find that we are welcoming and warm and generally worth knowing. We suspect you are too. So thanks for coming and welcome to Science Sunday. I did want to have a couple of potentials for announcements. I actually am taking this third Sunday when I usually take the first Sundays because I'm going to be gone in 2 weeks. I've already early voted, so don't worry about that. But we'll be in San Francisco, Jane and I, and we're going to a meeting of the Freedom from Religion Foundation, which we're members of and highly respect and like a lot. We're actually going to meet with Salman Rushdie. He's going to be out there speaking. Woman that did Letting Go of God. You saw that, Janine, with us, I think, right?
Julia Sweeney.
Julia Sweeney, thank you. And a number of other people. So it promises to be a good time. We'll be out there for a couple days. And then when that's over, we're actually going to get picked up by a van and ride through Sonoma and Napa Valley on our bicycles, or on bicycles that are supplied to us, actually. And,
no wine, all right? No wine.
No, we don't whine. When you're on a bicycle, there's no whining. But yeah, actually, I think the morning is basically riding, and then the afternoon and evening is recovering from the ride. So it should be pretty fun. So that's with a group called Trek Travel, and so we'll be gone for about a week doing that. Scott's going to have the next couple of Science Sundays, the first in November, taking over for me, and then the third is his regular time too. So that's what's coming up with there. Any other thoughts? Usually I try to remember to leave time for Stephanie, but she's not here today. I know she has her Just Views, which is another thing supported, another activity supported by the Humanists of West Suburban Chicago. And that's usually on the second Friday of each month, and talks about issues in social areas, legal areas, and so on. So you're welcome to come to that as well and talk to Stephanie about more information. The other thing is that today we're going to have a fire drill in any few minutes. So I would say grab your coat on the way out and don't get out there and get too cold. But make sure you bundle up. We'll all go out that back door. I'll have an announcement I'm supposed to make when we hear the bell. And so we'll gather up and go out there, and that'll kind of put a intermediate point in my talk today. So we'll see how far I get. I've got a lot to talk about. All right. So we'll all go out the back door and out and across the street. Okay. There's a secondary route if there is actually a fire. It has to go through the founder's room and down the steps there and out into the back, and then go around to the front again to meet up there. Okay? I always put these nice chairs up here for the circle of elders, I call them, and usually they're hit pretty much, but we're missing some of them today. So, let me get set up here ready. We're going to talk about an ocean of air today, or you called it a notion of air, or a motion of air is probably pretty appropriate. You didn't like lotion. Emotion? Devotion? Yeah. But I went with ocean, and hopefully it'll be explained why. Dawn, a new day here in northern Illinois. This portion of the earth rotates into direct alignment with the sun. We geocentric beings tend to call this sunrise. And all manners of cosmic rays traveling 93 million miles have direct line-of-sight access to all of us living things in this area. We'll visit this more deeply, but not quite yet. Most of this stuff, when you see this, it's impossible to put these things to scale, right? The size of the sun and so on. In my blurb talking about the atmosphere, I tried to make one point. If you take the Earth, bring it down to the size of a basketball, the layer of our atmosphere would be roughly equal to about 2 coats of varnish. And that's what supports us. But you and I swing our legs out of bed, because it just became dawn, remember? So we push our torso up, maybe not quite as quickly and as eagerly as we once did, and begin our day with a stroll down the hallway. We somewhat recognize we are residents of an immense sphere with a protective layer of air, but it certainly doesn't intrude into our daily thoughts. Again, from our geocentric point of view, we wonder how lobsters can survive immense pressures at ocean depths. But you and I very rarely realize or remember, we really are in a similar ocean, an ocean of air. There may have been one time in your life when you were immensely, deeply aware and impacted by the atmosphere around you. The moment you were born. What a change that was to come out into this atmosphere from a free-floating, weightless atmosphere. Anyone have any remembrances of that they want to share? Pretty shocking thing, though. You gasped and sputtered and grabbed your first breath of air. Earth's atmosphere. You were on your way. We do live in an ocean of air. We walk very much like lobsters on its bottom, but we are vastly dependent on all of its properties and qualities. So I wanted to kind of go into 3 areas, and I'm sure we're not going to hit them all today, especially with the fire drill impinging, and so we'll catch up on it later at another time. But one is, what is atmosphere made of? What is the layers and structure of the atmosphere around us? The second one I want to talk about is, do you know what elements and compounds our atmosphere consists of? And how was that discovered? How were those things found out? Pretty interesting stories there. And the third is what I've alluded to a bit here, air pressure. Things going on there. I'm pretty sure some of the demonstrations and things I want to show about air pressure we'll have trouble getting to today, but we'll see how it goes. Whatever we didn't miss here, we'll pick up at another time. So we can think and understand the layers of the ocean pretty easily. Different creatures are evolved to live in different areas. But how is it that we can't go down? There's something like an increase in pressure of 10 times for every 1,000 feet you go on. To the level of the depth of the ocean, at 11,000 feet deep in places, it's sometimes around 1,100 times the pressure that we face up here. 1 atmosphere pressure here and immense pressures down there. And we think, how do lobsters do that? How do all these different animals and critters do that? And we don't realize that we're also in a situation, much the same thing. Our ocean of air is what we'll talk about for a little bit here now, too. Basically, lobsters were evolved to live at the bottom of their ocean, and we've evolved to live at the bottom of our ocean. Right? So just as a little bit of discussion, there's different people say different amounts, and some of these get split up into different areas, but there's a troposphere, and tropo means revolving. So that's revolving, the atmosphere there revolves with the spinning of the earth. Rotates really, I'm sorry. With the spinning of the earth. All life forms are in that area for the most part. And 75% of the actual molecules that make up the atmosphere are in just that portion. We'll talk about each of these a little bit more. The stratosphere above it, you've probably heard that word. That's where the ozone layer is, and 24% of the rest of the atmosphere there. So that's 99% in that area, right? 10 miles roughly for the first one, 20 miles out further for the stratosphere. The mesosphere, very cold. There's not a lot of atoms out there to catch the heat rays, the rays from the sun. Very few molecules. Sort of shooting stars, which really are meteors, are coming through there, and they burn up in that area. The thermosphere is even further, fewer molecules, but the temperatures can get up to 3,500, 2,700 degrees in some of these areas. Okay? Large temperature fluctuations depending on if the sun's hitting it or not. And finally, the exosphere. Occasional molecules gradually escaping into space. There's no real demarcation line for those, but this is just the way scientists tend to think of the different layers of the atmosphere. Some scientists believe the atmosphere or the exosphere goes almost halfway to the moon, and others believe it's much less too. So the troposphere moves around with the Earth. It's the first layer in the atmosphere. You can kind of see a level there, a layer that's artistically created there to give you an idea. There's some significant levels, areas in here that really make these things change. They may not always be at the same height in different areas, but there is a specific things that occur in this area, and they call those the pauses. And there's differences that cause the clouds not to keep billowing up so that they get flat heads on the top of them sometimes if they're up to the top of there. They call those the pauses, the tropopause or the stratopause, or the layers in between, or the levels in between those. Okay. Other things about the troposphere. As you go up in the troposphere, you're getting closer to the sun, right? So the temperature gets warmer? No. Actually, thinking in that terms, which is common, geocentric thinking obviously, is to take a similar equation. Let's say you live here in Illinois and you take 5 steps toward Australia, and now you expect that you should smell the smoke from a bushfire going there a little bit better, right? We're moving up, getting up in the atmosphere, but with 93 million miles, if you move up 1,000 or 2 feet, you're not really getting any closer to the rays of the sun at all, right? You're getting less protection from some of them too. That's why you can get a sunburn up in the high mountains when you're skiing or whatever. You can think of it almost as if you're at sea level, it's almost like you have a nice down coat on it, pretty heavy coat that keeps you warm, right? And that down coat is the atmosphere that's keeping you warm. As you move up and you have less atmosphere protecting you, it's like shedding layers of coats. So it's cooler up at higher atmospheres. There's less molecules of air protecting or warming up the sun and protecting you from that. Okay? So it usually drops fairly quickly, 3 degrees per 1,000 feet, I believe. And so it goes up, it changes pretty quickly. "75% of the atmosphere is mass, and 99% of its water vapor and aerosols are in the troposphere." So this is the area where weather occurs, right, for the almost complete part. It begins at Earth's surface and extends 4 to 12 miles, almost all weather. Height varies at the equator and poles. The equator, the height is 11 to 12 miles. At the poles, it's under 4 miles. Also varies with the season. It's low in the winter and high in the summer. So it's a very fluctuating kind of thing. This is comparing or showing the troposphere here, in which commercial jets fly up at the top levels of it to get the benefit of the winds that are blowing up at that level, and also to have less molecular air molecules to hit. All right. So the troposphere isn't that much higher, depending upon where you're at, but than even Mount Everest, right? Most clouds are in this area. Okay? The stratosphere goes up. Weather balloons go up into the stratosphere. There are some very light clouds that fly in, that are in the Arctic regions that are there. The ozone layer, which is very important for us, is up here. Ozone down here is not helpful to us. Ozone up here is very protective. And also spy planes can fly up in that kind of zone, 15 miles up. Okay? This is a line showing temperature gradients. Okay, so temperature can decrease as you go up through the troposphere, and then it's fairly static through the stratosphere. If anything, it would increase maybe. You could get up to the top of the stratosphere in an elevator that takes you up to any of the tall buildings, Willis Tower or anything in Chicago. You could get, it's not that far. You could get from there up to the top in about 20 minutes, traveling at the speed of an elevator. You would not want to do it, however. Your organs would be crushed. Everyone would be in severe pain very quickly going to that amount, even just traveling at the speed that an elevator does. But it's not that far, but significant changes. Okay? Coming out with the same troposphere, stratosphere, with some of the same pictures. You can see that there's slight increase in the stratosphere as you get up near the top, and then some pretty big changes in temperature as you go into the mesosphere. Mesosphere is known as where they call them sounding rockets, the first rockets that never go into orbit get up into that area. John Glenn went up in a rocket like that early on. Some of you remember that. Most rockets nowadays are going to that level. I kind of wanted to get a picture of what flies or what goes at each level for you. Meteors are caught by the molecular structure here. As obviously the closer you get to the Earth, there's more molecules in each, and there's enough molecules and things in this area, ions and stuff, that capture meteors. So when you see shooting stars, they're shooting through this mesosphere. Some odd shapes of clouds, and sprites are pretty interesting things. Sprites are actually positive reactions, positive flows of energy underneath or above thunderstorms. So when thunderstorms are occurring, at times there's a positive force of energy going up while the negatives are going down toward the ground. This is a reverse kind of that, and it makes some pretty amazing things. They haven't been photographed much, but if you go on YouTube and photograph sprites in the mesosphere, there's some pretty good YouTube to show them. Pretty fascinating. They look like firework displays almost. But very beautiful. Generally reddish in color. Right. Can get to about minus 130 degrees. It's just that there's less and less molecules for the sun that's heating to each of them get their heat factor. Right? So there's less and less heat in this area. So this again shows some of the different things that fly in these different areas. Finally, past the mesosphere, you get into the thermosphere. And the thermosphere is called that because it can get up to 2,700 degrees Fahrenheit. It gets there, and it gets there because there's not protection of the sun's rays, but the molecules that are hit are very greatly impacted. But there's so few molecules that you could actually live in 2,700 degree temperature there. It's just that there's not enough molecules around there that actually will impart heat to you. So it's kind of an odd thing. All right, so we have exit through the rear doors of the Learning Center, out the foyer door, and cross the street, please. Anyone that needs help, stay in your seats and I'll walk with you. Anyone that can stay with me and go down from there. And then we'll come back. why there's so many molecules? In some areas, why it's denser and less dense?
Diminish.
I think it's gravity, basically, attraction. Yeah.
I'll get singed to make sure my friends are okay. All right. One score to reach. Yeah, there's a couple more. Yeah, if there were a real fire, that might be different.
We passed, we all made it.
Yay.
Well, that was nice that it was short like that. Yeah,
Yes, very well.
everybody's eyes aren't fluttering so much.
I did. It was like in the same spot. I've returned to normal.
So Scott, you kept photographs of how everyone performed, it will be analyzed?
Yeah, we'll be analyzing that.
It's like you haven't moved.
I know.
No, yeah, about the lies. The anal about the lies. Couple of interesting points were brought up. One is the success of early radio waves, radio signals. And Scott, if you have more knowledge about this, feel free to jump in too. But Marconi, when he was inventing wireless systems, because of the curvature of the Earth, he felt like radio waves would only travel short distances, maybe 100 miles, something like that. And he was continually underestimating what was actually happening. These radio waves travel much further. So the only way he could decide to solve that or explain it was that radio waves must travel in a curved path, because it explained the data.
Charged particles in the upper atmosphere.
Right. So he actually was trying to push and get more. He set up and actually put a station. He was putting higher antennas, and the signals are traveling farther than he anticipated. But it ended up with a transmitting station in England, and he, in the middle of winter, went to Greenland, I believe. No, it was on the Canadian shore, Nova Scotia, yeah. And so he set up a receiving station there. And I don't know the exact distance, but it's probably 1,400 miles, something like that. And actually they received the signals. And it was amazing, even, that it worked. And basically what was occurring, like was said, was that the signals don't travel in a curved path. That's not very scientific. Radio waves travel in a straight line. But what they do is they leave the Earth in a point, come up and travel in all different directions, but some of them would travel in a way that they would hit the ionosphere, which is another term for parts of the mesosphere, hit there, and obviously this is not the scale again, but it would hit there and bounce back. And some would end up received in Nova Scotia. Okay? So there are, it's kind of, you kind of think that in one sense you'd say, well, these are kind of fluid, flexible zones. There's just a few less molecules out here because of gravity than there are down here. But there's actually some very significant occurrences that happen in these areas. There's a tropopause, like I said, that stops weather clouds from going higher. And then up in this area, there's the ionosphere and an ionopause that stops radio waves and sends them back. And not only that, but also rays that are coming in from the sun, like I talked in my introduction. They're stopped in these different areas, and asteroids and all different things. So it's a very protective climate. Actually, there's been people that say that the amount of atmosphere that we have, stopping gamma rays, X-rays, ultraviolet rays, all the different rays that would be damaging to us, is equivalent to about 15 feet of concrete. You would have to have 15 feet of concrete to stop the rays that come through the Earth's atmosphere. Russell?
Yeah, you mentioned the temperature of the thermosphere as being very hot, but I don't know how molecules or you would feel it. So when they're working on that space shuttle, to see the space shuttle there, are they cooling the suits or heating them? What heat?
I just heard one of the guys that was out on a spacewalk, and he said that when he was out on a spacewalk, he could feel they were modulating the temperature. Let me start by saying that. He could feel heat from the sun on the right side of his knee and the cold from space on the left side of his knee. So, pretty interesting stuff. So there's very few air molecules and very little heat transfer is the basic concept there, okay? So this is a little bit of discussion. Where does the exosphere end? There's no clear upper boundary. There's no exopause or any kind of specific thing there. It does kind of peter out. Where the molecules are just gradually lessen and lessen as you get further and further away from the gravitational attraction of the Earth. So, like it says here, some scientists consider the outermost limit to be almost 120,000 miles, which is about halfway to the moon. For their purposes, that's what makes sense for them, right, as they define their scientific terms. I don't know that, that's not what we would tend to think of it, that's that far away. But some scientists, for what they do, they consider these are areas that have an impact on the Earth and do something that deep space doesn't do. Okay? This is an example of the protective aspects of the exosphere only, and others do other things as well too. The sun's rays, a solar wind comes in here, and there's all sorts of ultraviolet, gamma rays. You know, we think of light as the visible light that we see, again, because we're human-centered, right? Birds and butterflies, insects see ultraviolet light, and that's why some of their coloration that attracts their mates, we've talked about before in other Science Sundays, is visible to them but not visible to us. So the other aspects of light, all these other aspects of light that come in to the Earth are some damaging to us, some beneficial, right? And here's what they call a bow wave, just as there is in a ship. It pushes away things that would be coming in, the solar wind and the gamma rays and different things about that. I don't want to go too deeply into what does what because it's not that critical for us. But there's all sorts of different zones of what happens here. And here's the Earth, if you see it, just a little speck right here. And another part about it is not just the atmospheric zones about it, but the magnetic zones about the Earth too. Very critical, very important in protecting us. So these are all little lines showing the different magnification fields or the magnification field that protects us in many ways from a lot of these damaging rays as well too. Without that, we would be much more subject to asteroid hits, craters, meteors, different things like that. We'd be more subject to comets hitting and much more subject to all these different rays. So we'd have a surface similar to the moon if we didn't have an atmosphere. So I wanted to go in and now that we talked about the whole atmosphere, the zones and so on, if we talk and constrict it more to the troposphere, what is the troposphere? What does our area really contain? And there are, I kind of thought of like handing out things and saying to people, well, what do you think is in the Earth? But we got a new microphone here, and so I thought if anybody wanted to talk at question time or whatever, we could come up with some thoughts about this too. But what elements do you know what makes up our atmosphere, our air?
Mostly nitrogen.
Mostly nitrogen, okay, people are saying. Oxygen, critical for us. Is that the only atmosphere Earth has ever had?
No.
We've had a lot of different atmospheres at different times. Besides nitrogen and oxygen, carbon dioxide, argon. Argon is actually the third most prevalent gas. Water vapor, okay, good. And who knows what percentage, roughly, of oxygen there is in the atmosphere now? John?
Around 19%.
Right, varies 19, some people saying 21%, you know.
It's now 1%, so it's not stable.
Uh-oh. We should have an oxygen alarm practice, an oxygen drill. So if it's 21% or 19%, what's the nitrogen? What percentage is nitrogen? 70%?
78.
Yeah. If you take the two together, 78, the oxygen and nitrogen is more than 99% of the total amount in the atmosphere. And we're hearing about all this CO2, right? I thought CO2 would be coming up. 400 parts per million, roughly. We used to have, I remember being on a hillside making 200 of us people sitting there saying, we aren't going to let it get past 360, right? The hillside's still there, and we're still there, but 360 isn't still there anymore. But 360 parts per million, if you relate that to percentage points, it's 0.04% of the atmosphere is made up of carbon dioxide. So why is it that critical? What's that? It's a greenhouse gas, right? And greenhouse gas is a little bit of a misnomer when you get into it scientifically, but that's its term, right? It's very active. There were years of scientific study in which they were trying to find out why the Earth would get warmer or colder, and looking at it, and they made these atmosphere elements with air in it. People made large, terrariums, you almost say, with plants and animals growing in it. And then they take these they were so proud of them. Joseph Priestley had one that was a big reflecting lens, like this big, and he had paid a lot of money that his sponsor paid for him, really, to polish the mirror, and he'd heat up the thing, and nothing would happen. So when they changed to put more oxygen into there, when they had different amounts of nitrogen in there, none of those, they're such small molecules that they aren't affected by the increase in the heat from these things. But CO2 is a more complex molecule, and as is water vapor too. And those things, when they get excited, when they get heat added to them, they get they move very actively, and they create more heat, or they dissipate more heat. They store heat, and they cause a big problem for warming. Okay. So we know a lot about the makeup of the atmosphere, but back in the early Greeks, they thought air was one of the four basic elements, right? Air, fire, water, and earth, right? And earth and fire were pretty much seen to be more of a compound of a lot of different things, what the earth is, and one seemed to be more as a process, a fire process. But air and water both seem to have some qualities to it that seem to make them special. And it took until about the 1700s till people started isolating what made air air. Okay? Natural philosophers, even up into the 1700s, thought it was a single entity. So, how did the nitrogen get in our air, if we think of that? Any thoughts about how nitrogen comes up in our atmosphere? Early what?
Is the earliest atmosphere?
There were some very poisonous atmospheres early on, yeah. But it's a remnant actually of one of our early atmospheres. It's a remnant of the volcanic eruptions and the Hadean landscape that we lived in, with all the eruptions coming from the magma and so on from our Earth, and that's still there. It may have passed through a lot of life cycles of plants in that time since then, but it's still the nitrogen that was created 4 billion years ago, almost 3.5 billion years ago, at the creation of the Earth in the first Hadean atmosphere. So that nitrogen is still in our atmosphere, and it's about 80% of the total amount there.
By creation, you don't mean creation, right?
Natural process.
Let us pray. So Scott keeps me straight on that, and that's good. We'd have been off the rails long ago. Oxygen. How did oxygen get into the atmosphere?
I can't think of it. It's a growth, I believe. What's mass or something?
The mass of living things you're talking about?
I believe it's
Cyanobacteria and the early things that found a way to live after the planet cooled down to an extent. It was a waste product put off by cyanobacteria. And so that got added and added and added to the atmosphere. Okay? And it's fluctuated. Pardon me?
Bug farts.
Bug farts. I think those would be more methane, but I think it's plant farts, really. Plant respiration, right? As plants pull in CO2 and they put out things, right? They put out oxygen, so they're part of the whole process of
As soon as
photosynthesis.
it's CO2, you have oxygen. So the first microbes weren't using oxygen or CO2 because it didn't exist.
Right. Yeah, they were finding ways to metabolize the poisonous gases that we call them poisonous, but to them they found a way to survive on
A lot
them.
of it was in the ocean, so they were deep in the ocean, so it followed up.
sometimes at the hot venting down deep in the ocean. We got into that a little bit last year about the origins of life and so on too. Mhm.
The earliest animal bacteria were eating iron oxides, and the oceans were green. And they ate the oxygen and deposited the iron, and that's when we see all these masses, and that's these huge areas of iron. They're all come, the jelly come from that particular source.
Right.
And of course, when they gave up all the oxygen, they ended up killing themselves in their own pollution.
That's right. Yeah, and when you talk about up in Duluth or the different iron beds of amazing amounts, that's all the death of early creatures, right? Yeah. And giving that, for a while, the planet was red because of the rust that was, the oxidizing of the things that was given off too. Let's talk about that. Well, I wanted to, so oxygen is a pretty important thing, a critical thing in our respiration and our way of looking at life, but it also has some interesting stuff that was found out about it. I wanted to read a little bit about that. These guys, when they were the early scientists, they wanted to find out what was going on, and they would take a plant maybe and they'd put it under a bell jar. Maybe you remember that from some biology books, and they'd see what would happen to this plant, right? And if you put a plant in a closed area for a while, it's going to respire, and nowadays it would take in CO2 and put out oxygen, and sooner or later the plant would die, right? It would use its store of CO2, all right? Then they started getting kind of experimental, so you don't just want to work with plants, so they put little mice inside there too. What occurs to a mouse when you put it inside a bell jar of normal air? It uses up the oxygen and it dies, right? They were trying to time it, like wait until it passed out and took it out. There was a famous cave in Italy that people like to take little dogs to, and it happened to have a certain aspect geologically to it that air that it pushed out a little bit of CO2 out of the ground. It was over limestone, I believe, and it was kind of a depression in this cave. And people could walk around, and you'd be in an area where there was still regular oxygen, but they liked to bring their dogs there, and the dogs would run around until the dogs would pass out because the dogs had no oxygen down there. So, but the early scientists were doing these experiments, and so they saw that there was qualities in it that it needed, and then the next step was they put not a plant in there, not an animal in the bell jar, but not a person. Probably. They put both, a plant and an animal, right? And when you put a plant and an animal in there, what do they notice out of that? A level of equilibrium, right? Balance. That the plant put out the things that the animal needed, and the animal respirated the things that the plant needed, and they'd live a lot longer. Wow, that's pretty cool. So that makes them realize that that was the first inclination that there's other gases, that there's gases that make up air, right? It's not just one thing. There's a quality in air that makes plants thrive. There's a quality in air that makes animals thrive. And there's a quality that each gives off that makes the other thrive too. So this is the beginning of some of the understanding of the balance in the web of life. Right? So pretty important. But now, how do you get this stuff out of there? How do you find out what it is and how it is, you know? And you think of people in the to me, that's the fascinating part. How did people in the 1700s come up with this stuff? You know, we have all this education and books and everything else. And I was reading about this and saying, now how would I get oxygen out of this? And so I got away. And I have a jar here. Cap to the jar with a hole in it. Okay. And I'm going to pour a little bit of this solution in. You probably know what it is from the brown bottle. Hydrogen peroxide. Anyone know the exact? What is what is its chemical? H2O2, right? H2O2. Okay. This? Yeast. All right. Starting to grow up the sides there, if you can see. That's part of the foam of the H2O2. If it's making foam and rising up, does that imply that there's gas? Okay. This is a good day to have a fire alarm. You are ready to perform properly. So you get a little fire, a glowing ember. It worked at home, come on. There.
Ta-da!
Neat.
So what's happening here?
It's for oxygen is being,
Something that's just barely able to stay alive in regular air, right? Now gets put into this environment.
How long would that burn?
so the oxygen burns
Wow.
out.
How long would this burn? Oh, how long would the,
Yeah, is that essentially a lamp that can?
well, what's the limiting factor on this? Every time I'm doing this, I'm combusting more oxygen, right?
Yeah. What's gonna run out first, the fuel in the stick or the oxygen?
Looks like a long
The
stick.
experiments we could do with this, right?
Huh.
Don't burn your fingers.
Or the building. So, a good amount of oxygen came out of that, right? And chemists nowadays can talk about where the oxygen came from and so on. It's a little bit, this is not what Priestley was one of the first to isolate oxygen. He actually took a little chemical, a little metal compound, and he took his big refracting glass and he focused it on it. I can get the name of it, I forget what it was.
Wasn't
You
it
know?
mercuric oxide?
What's that?
Wasn't it mercuric oxide?
You are right, mercuric oxide, yes. Which is mercury and oxygen compound, right? And he focused his beam of his expensive refracting glass on it and focused it on it, and he created oxygen. So what did he do with this oxygen gas that he had? He probably played around with splints and blew them out and put them in and everything, but that's not enough. You got to do something else with it, which is what they were doing with the bell jars earlier, right? They put a mouse in there. The mouse was like running around. He was happy mouse. Everything was going great, right? He had much more combustion from the oxygen to keep that mouse active. The mice lasted a lot longer before they passed out, right? They were in the same volume of gas, but they lasted a lot longer. So that's a quality in air that they determined that is there, that makes, that we use in respiration, right? So oxygen is great. You see people at football games and different stuff, right? They run around, they get beat up, they go on the sidelines and they put an oxygen mask on, right? Or in hospitals to help people out. Why don't we up the atmosphere of oxygen? Why don't we do that in our climate and help out, right? There was a time that the atmosphere was at 30%, right? 40? I've heard of 30. You may be right. Dragonflies were like a meter across, right? Dinosaurs got enormous, right? It allows for great growth One problem with it, though, you know the problems of oxygen, too much oxygen taken in?
Burns really good. Burns really good.
It's actually burning. It's the same combustion in your body. When you respire oxygen, it's the same combustion. It's the same chemical reaction as burning wood, right?
Oxidation everywhere.
It's oxidation, right?
Imagine the forest fires, they'd just be infernos.
Right. You'd walk down the street and your heels would make a little spark and your feet would burn up. Actually, there's a lot. They can give oxygen to people for a while. People go to oxygen bars and they're in there for half an hour. Has anyone been to an oxygen bar here? Okay. You like the oxygen you got, right? Too much oxygen for too long. I mean, it gives you a burst of energy if you go to get some oxygen for a while. Very empowering. But too much, your lungs would fill with blood, you'd be combusting so much. It's the problem of free radicals. It releases free radicals, which you've probably heard of from everybody from Deepak Chopra talks about them, I think, to everyone else. But actually, that's a release of molecules that are very damaging to your system. So I wanted to read a little bit about that. Page 44. Breathing pure oxygen certainly feels good, but it's not necessarily good for the health. Priestley himself noticed the greater strength and vivacity of the flame of a candle in this pure air, and therein lies a warning. As a candle burns out much faster in oxygen than in common air, he suggested, so we might, as may be said, live out too fast, and the animal powers be too soon exhausted in this pure kind of air. He was right that breathing pure oxygen for too long can be dangerous. Half an hour in a Los Angeles oxygen bar won't do you any harm. But if you breathe pure oxygen for too long, your lungs would fill with blood, and after a few days, you would die. That's because the very thing that makes oxygen useful to us is also its greatest hazard. The oxygen we need to breathe is an exceptional releaser of energy. We need oxygen's reactive powers to enable us to live such vigorous lives. But even the diluted amounts that we breathe in ordinary air comes with its own perils. So, actually, the creation of oxygen, like John was talking about earlier, is what allowed for the single-celled animals to gain the reactive agents, the strength, the energy to make themselves into complex organisms. Without oxygen, oxygen is such an energy provider that it allows cells to go through the processes that make all the different parts that make you. Make your liver, make your lungs, make all the different, your heart, your brain, everything else. Before oxygen came in, there was not enough energy available for organisms to become multicellular. So the release of cyanobacteria, like Bill Daw was talking about, created the oxygen in the air, which allowed for this flourishing. When oxygen got up to a certain level at about 600 million years ago, that allowed for the development of the whole Cambrian explosion that we've talked about at times too. So, and the oxygen levels crept up and up and up from there because of the massive amounts of cyanobacteria putting out all this, and that led to the development of the Devonian period when the dragonflies were so enormous and so on too. So oxygen in our atmosphere is a pretty amazing thing. What it's done, and it's allowed us to be us. Without our atmosphere, without the oxygen in our atmosphere, we'd be in big trouble. Any other questions or thoughts about oxygen? We like it. All right. In back.
It's interesting that, people have acclimated their, or I guess, I'm thinking about people who live like in the Andes and how their bodies are able to function beautifully at that altitude, whereas if we went there, we would be very sick, I think, for a
Yeah.
time.
And it's a funny thing because sometimes very healthy young people go up to altitude and they get immensely sick, and their grannies or whatever are just hopping around checking out the sites or something too. So it's an individual thing. But yeah, over the course of time, we've evolved to live where we're at within a slight variation, right? We can go up 1,000, 5,000 feet and not feel too much difference. But even in Denver, people feel winded. I know I have a customer in Denver, and I go up there, and they've got this nice atrium, and you walk up 2 flights of stairs, you know, to see the engineering department. And I get up to the top, and they're starting to walk down the hallway, and I'm saying, wait a minute. So it is something, but you're right.
And that's all about the oxygen, right? It's not something else in the atmosphere
Well, that's not accurate.
Yeah?
It's pressure.
It's the pressure.
Right. If you go up 30,000 feet with oxygen on, you'll still pass out even if you have a mask on.
Okay.
Because you don't have enough pressure. It's one of the laws of physics about the exchange of gases within your body and out. And the pressure isn't enough to exchange the oxygen with what's in your body.
I would say at 30,000 feet, the pressure has a lot more to do with it. At 5,000, I don't think it has that much to do with it.
It varies as you go up. So at about 16,000 feet, you'll run into hypoxia. If you go up, as a pilot, that was the area
Yeah.
that you had to worry about. I've seen people go into pressure chambers and they just removed the pressure. They didn't remove the amount of air in there.
Mhm.
They removed the pressure, and people pass out and they put a mask on them and they can race back. They even know they were out.
Okay. I know that some of the elevations, like you were asking about, Jane, are somewhere around 4,000 meters. I think the highest, there's miners in the Chilean mountains, I believe, that live at they live at something like 4,200 meters high, and they actually work at like 4,800, but every night they go home because they don't like it up at 4,800. It's much better at 4,200. That's normal for them. But yeah, there are, the development of much larger sized lungs and much more capacity to carry more hemoglobin in their blood and things like that, and those are evolutionary developments. I know that there's no case, basically women can't bring a child to term at those high elevations, over something like 4,000 feet, that there isn't enough oxygen being passed through the placenta to be able to give the child the oxygen it needs to develop. So
4,000 meters, right?
Meters.
did I say meters?
You said feet, yeah. I was going to say Denver, it's true.
All right, thank you. Yeah, 4,000 meters, around 12,000, 13, 14,000 feet, right? 4,000 meters. Let me make that clear to all our Denver friends.
But you're a cyclist, so you would know about this. All the professional cyclists, they live at high altitudes all the time. They train at high altitudes all the time. So when they get down to things like the Tour de France, which is a sea level, they have huge oxygen capacities, and they can ride 200 miles in a day, and they do it for 3 weeks on end, and then they go over the mountains and everything else. Something that would kill us.
Right. Bikers are awesome, I agree with you. But there's actually a lot that goes on with that, too, that's the term blood doping, where cyclists and other Olympic-level athletes sometimes were accused of and often guilty of the fact that they would actually remove some of their blood 2 weeks before a contest. And they'd store the blood, their body would remake blood, and then the day before, or a few days before the contest, they'd re-inject that blood into their system, and all of a sudden they've got a lot more blood carrying around oxygen to their... And how do you prove that happened, right? It's nothing that can be tested for, it's your blood, right? There's nothing in there, so that was a big scheme. They call it blood doping, and it doesn't sound like the right term for it, but... By the way, if we could, maybe we should move more into... I've got a third thing, like I said. I knew we wouldn't get into air pressure, but I do want to keep these talks going. And maybe, Scott, you can hand some of these.
Quick comment, something I learned a couple years ago that was fascinating was that plants actually developed hemoglobin It evolved first in plants. And why would plants need hemoglobin to carry oxygen? Anybody have any ideas? To get rid of it.
To get rid of it, yeah.
Right. So hemoglobin first evolved in plants so that they could get rid of the poisonous oxygen from their tissues. Isn't that something? Anybody have any other questions?
Do your experiment.
What?
Do your experiment.
Yeah, do your experiment.
It's a demonstration. We don't call it experiments. I'll do one about air pressure right now, and show you something in that, and that brings into a whole topic that we'll have to talk at another time, but at least it'll give you something to think about, all right?
I just want to advise you, if you're going to use flame, you got a smoke detector right above you there. With water.
People will think it's another fire.
Well, you may get sprayed.
I never think these things through. But I do for science. Just to let you see a little bit what's happening here, I'm taking a normal, just a glass, a vial of water. Thank you. Filling it up as close as I can to the top.
What did you just put in there?
Watercolor, so that Jane can see it from the back, because otherwise I get in trouble. All right? So it's only there to help you see what's going on. And I have another little bowl of water. Things out of the way a little bit. This probably doesn't want to get wet. If I cover this up, the bottom is closed, and I put it into the water and remove my hand so that it's under the water, okay, there's this level of water in this jar will be higher than the bowl here, right? Than the level in the bowl. What's going to happen after that? After I let my hand out of there, is the water going to go out of this to make it all level? Is it going to stay in here? Is it going to, what's it going to do?
Stay.
Okay. It's going to stay
there unless you're 32 feet high.
Yeah, let it go.
Not so much.
There's an engineer over there.
Yeah. So,
2, 3.
all right. Why?
Because you need air
There's
in
no air pressure inside the glass.
There's two theories. Galileo was one that talked about it earlier on. He was experimenting with this after he was getting kicked out of the church or getting all sorts of trouble with the church for his other views of that we aren't earth-centered, right? He had to promise not to do stuff. So he got looking into this, and there's a lot of going on in the Middle Ages of getting water to places that you need it without big pumps and things like that. So siphoning was important, right? And so that you could imagine filling a hose up with water, right? Dragging the hose over a hill, making sure the water stays in it, leaving one side in a lake that you don't want, or a pond or a stream, and the other side in your field, right? And actually, there was a known fact, right, that you can pull the water, just like siphoning gas out of your car, you can water your fields, right? And Galileo was saying, well, that was because this was being sucked out, right? If you imagine if you have a milkshake and you have a straw and you're drinking a milkshake, you think you're sucking the milkshake up in your mouth. Sucking is a very, relatively understandable concept, right? That you can pull this stuff up. But it's not really what happens. Water pressure is not that. He explained it, for example, that if you'd have this tube, why doesn't the tube empty as it goes over the hill? You'd think that the water would each want to flow its own way, right? And he said, well, it doesn't do that because that would create a little bit of a vacuum. It starts to do that, but then that vacuum sucks that water back up in again and so on, right? So his whole concept, and most people's, And it's an easy way to think of it now, this is a sucking action, right? Things suck through there. Some lesser known people in him started trying to say that doesn't really seem to make that much sense. And they started looking at what was going on, or it made sense, but they didn't see it that way. They saw it as pushing. Well, what's pushing?
Yeah.
The atmospheric pressure we've been talking about, actually, there's about 14 pounds per square inch of pressure on you when I talked about when you wake up in the morning and push yourself out of bed, you're pushing against 14 pounds per every square inch just to get out of bed. We're used to it, we don't feel it, we're acclimated to it, like a lobster can walk on the bottom of the ocean. Us walking down there, we'd be crushed, right? But the lobsters are acclimated and involved to do it. So the guy wanted to look into this, and because he knew almost as much as Duncan, he realized if he was going to do this in a glass, he would have to have a glass that was
I don't know, 16 or 32 feet. I don't know
32
what-
feet high. Duncan was right. Which is also 18 Florentine L's, if you didn't know that. L's was their way of measurement at that time. That's not fun to work with, right? You have 32 feet. Can you imagine me trying to do this demonstration with 32 feet of tubing above me? Okay. So what can you do instead of water?
What would happen at 32 feet?
Yeah, why is that?
Thank you. It was known that siphons, if you went over a hill and wanted to water your field, if the hill was over 32 feet high, if that water had to go over 32 feet high, the siphon would break, right? Galileo said there was so much weight there that it overcame the sucking that was in between the holding, right? That was his whole theory about it.
Mike, I don't know if you've said this, but it's the weight in the water that's equal to the atmospheric pressure. So if you had a tube that was an inch square, and you had 32 feet of it, the weight of the water, of that 32-foot column of water, is the same, produces the same pressure at that inch at the bottom as the air is pushing on the rest of the water.
On the rest of this surface of this water in here, all right? And that had to be proved, right? That stuff had to be proved. And so he did this, and he set this up, but he didn't want to have a 32-foot tall tube and the damage, the problems that all caused. What can you do to make this an easier experiment? If you use a heavier liquid, right? So back in the 1600s, they used mercury, which we still talk about today in terms of atmospheric pressure, right? Mercury is about 6 times the weight of water, so he calculated it should be, instead of 18 Florentine L's, it should be about 2.5 Florentine L's, which is about 2 feet of mercury, okay? So he could get a 2-foot long tube, right? Make it whatever diameter he decided, and he did that, and he found that, like Duncan was implying, that no matter what diameter you used, the mercury still came to the same height, right? Because you have more weight in there, but the atmospheric pressure is pushing down to balance that, right? It's pushing up on more.
And then as weather moves through, you can actually see that fluctuate.
Right.
Yeah, well, that's where you get thermal pressure from, right? 29 inches of mercury.
So, just an aside, is the term life sucks just a description of the scientific process?
It's the pressure from the outside.
That's people at Griffin, Kansas City's outlook on life. So he was working with this, but it still didn't prove, this doesn't prove whether this little vacuum up here is sucking or not, right? It doesn't prove that or disprove Galileo's idea. It's showing that there's something happening here that keeps this up, but it doesn't address the question of the sucking of the vacuum that's up here or not. So he had to come up with a new experiment, which is what science does, right? He took another tube, and this tube he took was very much like this one, except he put a pretty good sized globe up here. All solid glassware, right? And he filled that whole thing with mercury. So it was mercury filled up all the way through this globe that was sitting up here. Okay? And the hypothesis, if you go by Galileo, would say that, well, as more of this flows out, you're going to have a big vacuum sucking things up, right? And with that big vacuum sucking things up, that's going to keep more of this up here, right? So the level should be higher if Galileo was right, if vacuum sucked, right? So he had this big volume up here, poured them both full of mercury, put them side by side, and was Galileo right, or was Torricelli right? Galileo was wrong. Torricelli was right. They came to exactly the same level, right?
So life doesn't suck.
Exactly. Exactly. Unless you're from Kansas City. But so that. What did I have? I had a finish on that, but I didn't. I lost it. Sorry. So he proved that out, that basically this is the pressure, like Duncan was saying, of water, of the atmosphere pushing down on this water that we don't even feel. You can put your arms out here, you don't feel 14 pounds per square inch of air, atmospheric pressure pushing on you.
Or compressing you.
Or compressing you. It's because you've evolved, right, through billions of years to be a creature that can withstand this. You put us down to the bottom of the ocean and we feel atmospheric pressure immediately, right? Pressure that atmosphere. But we're evolved to live in this atmosphere. We walk around on the bottom of our ocean, just like lobsters walk around on the bottom of their ocean.
Which is
the thing.
one of the dangers of a spacewalk outside of a spacesuit is that your body is accustomed to building an internal pressure to equilibrate. So if you're on the moon or out in space without atmosphere, essentially your blood would start boiling, and your body would fail because it has an internal pressure much greater than the ambient.
There was, I was thinking of starting out the whole talk with the guy that went up. I knew his name a few weeks ago, and I forgot it because I've been concentrating on other stuff. But he stepped out of a weather balloon at about 30,000 feet above, and he went down in the 1968 or something like that. He was up there and he traveled, he free fell for like 15 minutes or something like that towards the earth, and finally pulled his chute and came back safe. He didn't tell people when he was doing this that he realized when it was time to pressurize his suit that his left glove didn't pressurize. And if he told them, they'd have aborted the experiment. Somebody like Bob would have said abort the experiment. And so he didn't tell them. So he kind of held it as far as he could, and did what he could, and it swelled up. But when he got to land, it was like swollen to 3 times size or something like that. It took a while to recover and everything like that. But he got his experiment in. So, and then I mean that makes me think of like, why doesn't a lobster explode when you bring it up from the bottom of the ocean, right? And because they have things that are more adaptable and more able to recover from that. Okay, just their structure, maybe with their exoskeleton, and they've got water inside them that's supporting all their structures. So,
Would the lobster come up and that, you said bringing it fast, isn't there like the bubbles, the nitrogen bubbles that
The
we
bands.
get?
that's because we're breathing atmosphere, we're breathing air, we're breathing gas, right? And that gas and the nitrogen in the air that we breathe can get into our bloodstream, and then those bubbles expand. The thing about gas is it expands. It's something like 1,100 times the rate or something that liquids do. Liquids don't expand much. You know, brake fluid in your car, it's a fluid that doesn't expand. It stays the same, it just pushes. But gas expands astronomically. So when you take gas in your system and you go down and then back up again, that gas is turned into the nitrogen bubbles and they expand astronomically and you suffer the bends.
Was the same, or would be the same going both ways? Going down?
Well, they would tend to contract when you go down, the bubbles in your, so it's when they expand that they cause problems. And that's, the expansion happens when you're going into lower pressure, when you're rising through a water column.
When you go down, you don't notice as much. People have free dove to generally like almost 1,000 feet or something like that.
Yeah, we're not taking air in.
Because they're not, they go down and then they go back up. Yeah. Joanne?
For instance, 18 grams of water.
This is such an advancement, you gotta use it for science.
As for instance, 18 grams of water, when you turn it into a gas, becomes 22.4 liters of gas.
18 grams
18
is,
grams of water.
yeah, a few cubic centimeters, right?
Really small.
What's that?
Really small.
Yeah,
Becomes 22.4 liters.
which is 6 gallons, 5 gallons, right? Yeah.
So,
Yeah. That's, you don't want that to happen in your bloodstream. All right? There's animals like whales and seals that dive deep and how they do that. And I was just, this is all stuff that, you know, you start reading and you can just go down all these paths. And I was reading about how they acclimate to that and what they do. And part of it is the structure of how their lungs are constructed. I think it stops the alveoli and things in the lungs. They actually contain, when they breathe in, the air goes almost immediately into their bloodstream and into their organs. We keep it in our lungs, right? But it's there in their organs, and somehow they're able to adjust for that and not get the bends when they go deep and come back up.
Spring wet, down 5,000 to 6,000 feet.
Yeah, it's amazing. So, any other thoughts or questions? All right, well, thank you guys for not,
Thank you, Mark.
with the what? No, this wouldn't collapse, I could do it much bigger. So that's, I'm not going into the balloon at all, but I can make it expand or contract. Well, it depends. The person is somewhat individually, you know, accountable for what happens to them. But, you know, I mean, people actually train in those elements, right? The skiers and runners. And like I said, sometimes it takes a very and just there's enough oxygen to keep it, so adjusting your system, I guess, to be able to your system adjusts oxygen. Everybody's different.
That's